Hello, this is part two of initial value problems. In this video, I will go over more over interval of existence and determine where a particular solution is defined, continuous, and differentiable. Okay, so interval of existence, existence of a unique solution to, uh, to be rectangular region in the xy plane defined by a is less than or equal to x, less than or equal to b, where c is less than or equal to y, less than or equal to d. Contains the point x naught, y naught in its interior if f of x, comma y, and delta f over delta y are continuous on R, then there exists some intervals I naught of x minus h, comma x naught plus h, where h is positive, contained in intervals a to b, and a unique solution function y of x defined on I naught that is a solution of the initial value. So what does that really mean? It just means you can almost think of it as a domain, right? You can almost think of this your solution will be like in a domain. And let's do one problem. So so how do you find the interval of existence steps? Find the arbitrary constraints using initial condition. Write a particular solution. Determine whether the particular solution is defined, continuous, and differential. Find the domain. Choose the interval from step 3 that contains the initial condition. So let's do an example. So example 5 says, determine whether the uniqueness/existence theorem implies the given initial value problem has a unique solution. So on part A, we have dy dx equals y to the fourth minus x to the fourth, where y of 0 equals 7. So what we're going to do first, well, y of 0 equals 7 is a coordinate. It's like 0, 7. And first we got to determine if f of x comma y is continuous when you plug in 0, 7. So first step is continuous when you plug in your point. So so let's see. So we have dy over dx equals y to the 4 minus x to the 4. So we have an x coordinate of x. I mean, an x coordinate of 0 and y coordinate of 7. Let's plug it in. So y is 7, so that's going to be 7 to the 4 minus x. 7 to the 4th is a number. So it is continuous because it's not like 1 over 0, right? Right? We don't have a vertical asymptote. It's not a rational function. So it is continuous. So what about, so the next thing you have to do is delta f over delta y continuous when you plug in 0, 7. So is delta f over delta y So delta, so what is that? Delta f, what is delta f, delta y? So I was just looking at our rules. So is delta f delta y continuous? So basically you take the derivative in respect to x. I mean, to respect to y, right? So our equation is f of x comma y equals y to the 4th minus x to the 4th. So if we take the derivative in respect to y, that means what that really means is anything that doesn't have a y doesn't really matter. So that's like ignore it, or you could think of it as a constant, right? So this x to the fourth isn't in terms of y, so just ignore it, right? It's not really important. So the derivative in respect to y is basically the derivative of y to the fourth, which is 4y to the third. And then if you plug in the coordinate f of, oops, f of y of 0, comma 7. So what we're doing is doing partial derivatives. So we only got to plug in our y value because we don't have an x anymore. So it's 4 and then replace y with 7. So that would be yes. So that just means it's unique. Yeah. So on part B, so we know it's continuous and we also know it's unique. So what do we do next? Wait, what is it? The direction says determine whether it's unique or existence there. Okay, so we were just determining if it's continuous and if it's a unique solution. So let's do part B. Let's see if we have dy over dx equals 3x minus cube root of y minus cube root of y minus 1, and then we have y2 equals 1. So that's like a coordinate, 2 comma 1. Here's your x, here's your y. So let's see if it is actually continuous by plugging in your coordinate. Okay, so go ahead and plug in your x and your y. So this would be 3 and our x is 2 minus cube root. And our y is 1 minus 1. So that would be 3 times 2 is 6 minus the cube root of 1 minus 1 is 0. So that's like the cube root of 0. That would be 6. So it is continuous. Okay. And then we got to check if it is unique. So we take the partial derivative. So you could think of it as f of x comma y, 3x minus, I can rewrite the cube root of, I can rewrite the cube root of y minus 1 as parentheses y minus 1 to the 1/3, right? Okay, so what I'm going to do is take the derivative. I'm basically taking the partial derivative in respect to y. So f of y. So this 3x does not have a y, so you can ignore it, or you could think of it as a constant, and the derivative of constant is 0. Now, how do we take the derivative of negative parentheses y minus 1 to the 1/3? Yes, you can apply the power rules. So it's going to be, this has a coefficient of -1. So -1 times 1/3 is -1/3. Leave the parentheses alone. And then it's just whole power minus 1. So whole power is 1/3 minus 1. And in our case, it's like 3/3. So that's 1 minus 3 is -2/3. And then take the derivative of the inside. So the derivative of y is 1. So that really is, you simplify that, that could be expressed as -1/3. And then you have y minus 1 to the 2/3. Oh, yeah, so I just made this negative exponent to a positive. Okay, then what I would do is plug in your coordinates. Our coordinate is 2 comma 1. And I think all we have to do is, I think we're just going to use our y value. There's no x. 1 minus 1. Then you have -1, and then this is 3. And then what's 1 minus 1? 0 raised to 2/3. Okay, we kind of have a problem because this 0 to the 2/3, and if you do the bottom, 0 to the 2/3 times 3 is actually going to be 0. and then you have -1. So that would be undefined, and that is no longer unique. So it's not unique, but it is continuous, not unique. Okay. So on this example, we just determine if it's continuous or unique. So determine if it's continuous, you simply plug in your coordinate. If you actually get a real value, like 7 or 9, or that's continuous. If it's undefined, it's not continuous. And then to determine if it's unique, you take the partial derivative in respect to y, plug in your coordinate, and if you get a real number, it's unique. If you get an undefined number, it's not unique. Okay. Example 6. So example 6 says, give the largest interval I over which the solution is defined. Give the largest interval I over which this solution is defined. We have y equals 1 over x squared plus c, and then we have y prime of 2x y squared equals 0 with an initial value of y of 2 equals 1/3. So you can write this as a coordinate if you want. That's what I'm going to do. What would I do first? So from the previous problems, I would solve for my c, right? So how do we solve for a c? By plugging in your initial value. So 2 is your x and 1/3 is like your y. So go ahead and plug that in. So plug it back into this equation. You replace y with 1/3. Replace your x with 2. So that's going to be 2 squared plus c, 1/3. And then 2 squared is 4 plus c. Your goal is to solve for c. So I'm going to cross multiply. So 1 times 4 plus c is just itself. 4 plus c equals 1 times 3 is 3. Go ahead and solve for c. So I'm going to subtract 4. Yeah, c equals to 3 minus 4 is -1. Okay. Now we can plug it back into your this equation, right? Your original equation. So it's going to be y equals 1 over x squared plus my c value, which is -1. So instead of putting plus, I put -1. Okay, I'm going to box it. That is not our answer. Remember, they're asking for the largest interval. So what you would do is find the domain of this equation. So what kind of equation is this? This is a rational equation. And how do you find the domain of a rational equation? It's basically all real numbers except for the vertical asymptote. So how do you find the vertical asymptote of a rational function? You simply set the denominator to 0 and solve for x. So our denominator is x squared minus 1. Set it to 0, solve for x. I get x equals plus or minus 1. So that's what x cannot be. So what we're doing is trying to find the largest interval where the solution is defined. So what I would do is it's kind of hard figuring this out without a graph. So I would graph this function, and then look where the point 2 comma 1/3 is part of your graph. So let's graph this. So we know our vertical asymptotes are x equals 1 and x equals -1. And then let's find our horizontal asymptote because it is a rational function. So how do you find what is our horizontal asymptote of this particular rational function? So you basically look at the highest degree on the numerator and the highest degree on the denominator, right? The highest degree on the numerator is 1, or really life can also be expressed as 1x to the 0. And then your highest term on the bottom is, or your highest degree on the bottom is x squared. So there's three rules. This is specifically bottom heavy. And what do we know about bottom heavy? It is always going to be 0. Our horizontal asymptote is y equals 0. Okay, then go ahead and start you can start graphing because now you have your your vertical and horizontal. So go ahead and start graphing. Okay, so let's graph our vertical asymptote, which is x equals 1. Here's one of them. A dash line. And yes, you can also put this in Desmo. And then your other vertical asymptote is -1. And then your horizontal asymptote is y equals 0. Let's use a different color so you don't get confused. So how do you express how do you draw y equals 0? It's like this. Okay. Then what you could do is plug in some points. So we have to test the right, the middle, and the left, right? We have the right side, the middle side, and then the further left. So let's test the point. So we can't use the x value 1 because that is our vertical asymptote, but we could use the x value 2. And go ahead and put that in your original equation. So do y of 2. 2 squared minus 1, so that is 1 over 2 squared is 4 minus 1, so that is 1 over 3. So you have a coordinate at 2 comma 1/3, which is technically, it is about 0.3. Okay, go ahead and plot that. So here's 2, 0.13, here's 1. So you know it's not going to cross the red dash line or the green dash line or this other dash line. Maybe right about here. So on the right-hand side of the graph, it's going to look like this. Careful not to cross any of those asymptotes. Let's do the further left, region 3. So I can't use the x value -1, but I definitely can use x value -2. Go ahead and plug that in. So -2 squared is 4 minus 1, which is 1 over 3, which is about 0.3. So you have a coordinate at -2, comma 0.3. -2 is 0. Here's -2, and 0.3 here's 1. So it's about right about here. And then just do this one. Okay. Then what we're going to do is do the middle part. So the middle part is can't use 1. We can't use -1, but I definitely can use 0. Let's do that. Let's do 0 squared minus 1, which is 1. So you have a coordinate at 0, comma -1. Here's 0, here's -1. And I have a feeling it's just going to be a downward parabola like this. Because I know it won't cross the green dash line, and I know it won't cross the red dash line, so it has to be concave down. Okay, so what is our largest interval? What would be our largest interval in which the solution is defined? So you got to figure out, we have the graph right here, right? Now, our solution is at 2 comma 1/3. So 2 comma 1/3 is right here. So so we only care about region one, right? And how do you express region one as an interval notation? It's basically from the intervals one. So you could say the interval of existence where our solution is, which is at 2 comma 1/3. Is that region one, which could be expressed as parentheses 1 comma infinity. So this is the largest interval of existence, which is at 1 comma infinity. So, but if you really want it, the domain for the entire graph is all real numbers except for the vertical asymptote. So let me write that out. This is not our answer. I just want to make sure that the domain of this graph is all real numbers except x cannot equal -1 and +1. So how do I write that as an interval notation? It would be from -1, -1, union -1 to 1, union 1 to infinity, right? So that so what we do is look at the coordinate, look at the point where we have, or our solution, which is 2 comma 1/3, and then that only leads us to 1 to infinity. So these doesn't really matter. So yes, I would first figure out the domain of your graph and then just eliminate which one isn't part of your solution. Okay, so that was that one. Let's do one more example and then okay, example 7 says give the largest interval I over which the solution is defined. We have y equals c of absolute value of x times dy over dx equals y, and we have a given initial value of -2 comma 6. Okay, so first step is figure out what the c value is by plugging in your initial value. So -2 is x, 6 is your y. So plug it back into this equation. So it's going to be 6. The absolute value of x, that's going to be c6 equals, and then the absolute value of -2 is +2. Whoops, why did I put a 6? This should be a c. And then go ahead and solve for c by dividing both sides by 2. So c equals to 3. Okay. What you could do, so now let's find the domain of this graph. So our equation is y equals 3 of absolute value of x. So how do you graph this? Well, it's an absolute value graph, so it makes that, we all know the absolute value makes that V shape. But the thing is, our slope is, we have this 3, so it kind of makes it a little bit skinnier, if that makes sense. So you could make a table, or you could think of this 3 as your slope, like 3 over 1. So let's go ahead and graph it. Okay. So uh, So our slope, so what you would do is to graph this, you could start at the origin and then 3 is like your rise, and then 1 is like your run, right? So what you do is go from the origin 0, 0, start in the middle, and then go up 3, 1, 2, 3, and then run to the 1. And then do the same thing, but do it on the left side. So go 1, 2, 3, and then left to the 1. So if you connect those dots, it would look something like this. So it is slightly skinnier than the absolute value of x. Okay, so if that's our graph, what would be the domain of this graph? So the domain of our graph is from negative infinity to positive infinity. Uh, where is it continuous? It is continuous basically everywhere, all real numbers from negative infinity to positive infinity. What about where is the interval where it is differentiable? So if you how do you determine if something where is it how do you determine where is it differentiable? So you cannot have any cusp or like so this is like a cusp. So it can't be differentiable in this area. So you could say it's differentiable from here, this region, and then here. So that would be from negative infinity to 0, union is 0 to infinity. So where would be our largest interval of where would be our largest interval of existence? So so keep in mind, let's see, our point is at negative 2 comma 6. So where is negative 2 comma 6? Negative 2, 3, 4, 5, 6. So it'd be right here. Let me use red. Right about here. Okay, so where would be, that means we only care about this region, the further left, because that is where our solution is at negative 2 comma 6. So we only get to rely on region 1. And in region 1, it would be expressed as an interval as negative infinity to 0. Right? And we don't really include 0 because of this cusp. That's why I use a parentheses. Good. So this would be our largest interval of existence for this initial value problem. And that's it. So I'm going to stop here.